In this video, I will be trying to continue the discussion on tensors. In the previous video, I already gave a nice description of chart transformations and how vectors actually don't transform. How vectors change in different kind of chart transformations, but actually in reality a vector is just a vector, and how you present it in different charts must not qualify its vector properties. So now in this video I will be discussing more on why a vector is a tensor and what is the transformation property of a tensor. So I will just give a brief overview. So we initially start with a set. So we start with a set M, and then we give it some sort of a structure to make it into a topological space. And then once it is topological space, we define the notions of continuity of functions over that. And then further, if you want to add more structure of differentiability and smoothness, or talk about smooth functions, we define something called as a manifold, which over this topology we add more structures, local homeomorphisms to RD. And then from manifolds we define charts and atlas, which is just the coordinate maps. And then finally we arrive in something called as a smooth manifold. So you can think always of a sphere, that locally how a sphere looks a two-dimensional plane and a sphere is a two-dimensional manifold. So anyway, now given you have a manifold, we let's look at this thing. So from the real lines, we take a curve gamma to a subset that belongs to the manifold. So that belongs to the manifold, and then we bring down using charts. This is like the polar coordinates or Cartesian coordinates, where x is the chart map, and we lie in some RD if the manifold is of deep dimension. And then you have a function which is a smooth function C infinity m, infinitely differentiable, and we go to R. So and now we have this line here and this line here, and this this function is just gamma ox, and this function here is just x inverse of f. And this is the basic this is one of the most important diagram, I feel, whenever you have to remember anything, because we start with asking directional derivatives. So given a manifold and a curve, so this is gamma, the curve, you ask that what is the directional derivative, in the essence like what is the velocity vector to the curve at a point P, and that is basically a map. That is a map which is defined to a curve at a point, and what it does is it eats continuous functions and maps them to, so f of gamma. So first you apply gamma, and then you have f, you differentiate, you derive at a point 0, such that by definition you choose that gamma of 0 lands you to the point of interest P. So and now this is the way of defining the directional derivatives to the curve, and then one can easily see that f o gamma derivatized at a point 0 can be by using the chain rule. We can just write it as differential I f of x inverse, and then you have xi of gamma, and then this part you can just define it to be del of xi at a point f to a curve, and this part will be now gamma dot of I. So this is where we ended in previous lectures, and I quickly showed it again. So the the fact is that the directional derivatives to occur whenever at a point on the manifold is just of the form it is of this form. So, and further we discussed the fact that these things here are the basis vectors, and these are just the components that any vector has whenever it is written in the basis formalism. So from here now we quickly take a look at what is the transformation properties from one chart to other of these vectors. So 1-0 tensors are just vectors. How vectors, so now vectors belonging to the TPM, which is the tangent space at a point P, changes under coordinate or chart transformation. So this is simply the fact that you can, if you have the three-dimensional real world, you can bring it to a polar coordinate or you can bring it to a Cartesian coordinate. So this is what we call as different coordinates or charts. Now any vector, as I showed just now, can be written in this form, where del xi at a point P is just the basis set. It is just a basis set to the space of these vectors. So vectors, a vector space has a basis with respect to which we can write the components of the vectors, and obviously the basis is not something unique that we can see, because this x is the coordinate chart, and I can choose a different coordinate chart to represent this vector again. Now let's see the transformation property. So I will first let's try to transform the basis set. So del xi of a function f by definition is defined like this. Now this is x of x, this is f of x inverse. Now I will just introduce a identity here. You can see this part is just the identity function, and then I will just use the chain rule. So the chain rule, you can see here there is a summation implied on the j, and the I is still now carried from here to here. So this is this. Now by the very definition of del xi, you can see this part can be transformed into this definition. So into this definition, and then on this side you have this part here, which can again be transformed by the similar definition here into this. So the definition that I am using is this del xi. So let me just write it here. Del xi of a function f, which is a C infinity m, or a smooth function that maps from the manifold to the real line, is defined to be differential I. You see this is the definition, f of x inverse at a point x of p. So f of x inverse in this diagram, you see it is this map from Rd to R, and I will like we can if we remember this diagram, it is very easy to see why this definition is obvious, which I derived in this part. So now let's look at what is the transformation property. So from here, inserting an identity, we come to this line, and here you see that if I omit the the C infinity m function, you see del xi changes to del yi by the Jacobian. This is the very Jacobian that we are generally used to in most of the physics problems of coordinate transformations. So that is quite obvious that it will show up, because this is the more fundamental definition of why two different basis sets are connected by a Jacobian. So now I will just rename. So del yj, I will call it as del j prime, and then del xi I will just call as del I, just to reduce the notation. And then you see this part will be j prime and it will come down here. So this part here that you see is what is the transformation property of the basis of a vector. Now that is given that, now we must always we must understand the fact that any vector is a vector. So any vector is a vector. What does it mean is that a vector does not care about which basis you choose. So a vector can be written in the xi basis or yj basis, you see. So I have just changed the summation index here from here to here. Now if these two are equal and I have the property that how del yj and xi are related by this Jacobian, I can write this here easily. Now for this and this to hold, you can see that this is just the xi component. So at this point we have managed to transform the basis as well as the components. So and this is the two properties that I have shown here. So this is the change of the components of the vector and this is the change of the basis of the vector. So one of the nice way to remember the formulas of transformation is that, so you have a basis del xi and you need to transform it from a basis of y. So whenever you have y, the first thing is that y must get summed over. So I put a y here, so that they get summed over, and here you have I. So you see, you can just intuitively construct the entire proof that we just now did. And similarly we can do for the x part, that the fact is, because of the Einstein's summation index, the x part will have an index upward. So now you will put a j here, you will write a y here, but y must get summed because at last I should have x, and then you should have del yj del xi. You see, these two are the two ways in which the coordinates and the components transform, and one can see that they actually transform in the exactly opposite manner so that the vector actually remains same. So this was the how the transformation is obtained of the vectors, and you can see that there is a small example here. It is just the Lorenz transformation. So the Lorenz transformation that we know can be said to be a transformation that goes from the x basis to the y basis via this Lorenz matrix. And then you simply see that Lorenz matrix is nothing but the Jacobian of the charts of x and y. So from an inertial frame to when you boost, so from an inertial frame to a boost along y direction or x direction is actually a chart transition performation. So that is what the Lorenz transformation gives us. So that's all for this video. I hope this was clear. So one of the important thing to remember is the diagram that from R you go to the manifold M via a curve, which is a trajectory. From the manifold you go via a C infinity M function, you go to the real numbers again. From manifold you come to the dimensions Rd using a chart, and then you just want to link them in this formalism of tensor space. So this function is just gamma OX. This is just X inverse OF, and then from here you can construct the necessary requirements, whatever we need. So that's all for this video.